This is a continuation of the video 7.3 about sampling distributions of sample means. This is an example. A bank in a small town has to stock a single automated teller machine, an ATM, with cash at the beginning of each day. Based on thousands of transactions in the past year, they know that the average amount of money requested by a customer is $87, with a standard deviation of $52. The distribution of money requested is strongly skewed to the right. The bank estimates that there will be 50 customer requests for cash from the ATM each day. The bank is trying to decide how much total cash should be stocked in the machine at the beginning of each day. So for part A, calculate the probability that a random sample of 50 customers for cash would require a total of $5,000 or more, or an average request of $100 per customer. Now you might try to start with the total. So I've got 50 people, so that's 50 x's, and the mean for the total would be 50 times the mean for one. So that would be 50 times 87, or $4,350. We can find the standard deviation using the formulas you learned earlier, and that'll be the square root of 50 times the variance, and that's going to be 50 times 52 squared, square root, that's $367.69.55. The problem with this distribution is that it's not normal. So even though we've got the mean and standard deviation, we can't go to the normal distribution for calculations. So instead, we turn to means. The mean of the x-bars is $87, and the standard deviation is 52 over the square root of 50, or $7.35 with 79 hundredths. Since there are more than 500 bank customers in total, that formula is just fine. Even though the population it's strongly skewed to the right, since n is 50 and that's more than 30, the sampling distribution of x-bar will be approximately normal according to the central limit theorem. So the probability that x-bar is greater than 100 is just a normal calculation. We use normal CDF with a lower bound of 100, an upper bound of something very big, a mean of 87, and a standard deviation of 7.3539. And that gives you 0.0385. Now, it is true if I calculated it with the combined data, the combined values that we computed first, I'd still get the same answer, but we use the means because of the fact that the normal distribution holds for that situation. So, as a side note, as indicated in the previous example, problems involving totals can often be solved with means and vice versa. For example, to find the probability that the total weight of 4 men is greater than 800 pounds, either you can use the formulas for combining random variables and treat it as x plus x plus x plus x, and therefore finding the probability the total is 800 or more, or you can find the probability that the mean weight of the 4 men is greater than 200 pounds, since 800 divided by 4 is 200, and calculating the probability that the mean is greater than 200. Okay, so let's look at the next part. So same bank, same situation. How much money should the bank put in the ATM to be 99% certain the machine will have enough money to satisfy a random sample of 50 customer requests? All right, so the key is to figure out what they're asking exactly. If we're 99% certain that the machine has enough money, then what we're saying is the machine will have enough money 99% of the time. In other words, find the 99th percentile. All right, so we had a normal distribution because of the central limit theorem. We know the mean for the x-bars is 87. We know the standard deviation. So we're trying to find that x-bar that you see in the picture. Well, you can use inverse norm. You've got the area to the left was 0.99, and you know the mean and standard deviation. So that means that x-bar is at 104.1077. The bank should have an average of 104.1077 per customer. They're planning for 50 customers, so multiply that by 50. They'd need $5,205.39 each day. All right, now here's one for you to try. Mr. Rose is a new quality control inspector at a factory that produces axles for a certain model of car. Because the manufacturing process takes several steps, there is some variability in the length of the axles produced at the factory. Specifically, the distribution of axle lengths is normal, with a mean of 597 millimeters and a standard deviation of 5.3 millimeters. Mr. Rose randomly selects one axle. Find the probability that the length of the axle is less than 595 millimeters. All right, well, since we're dealing with one axle from a normal distribution, we can calculate this pretty straightforwardly. The probability that x is less than 595 is just normal CDF. Lower bound of something really small, upper bound at 595, the mean is 597, and the standard deviation is 5.3. That gives 0.3530. In other words, there's a 35.3% chance that the length of the axle is less than 595 millimeters. All right, here's part B. Mr. Rose randomly selects 20 axles. Find the probability that the mean length for the axles is less than 595 millimeters. Since we're dealing with 20 axles and looking for the mean, we need to determine if the sampling distribution of x bars is normal or approximately normal. Since the population is normally distributed, we know the sampling distribution is also, and there's no need to use the central limit theorem. Now we need to meet the 10% condition in order to use the standard deviation formula. In a factory producing axles for a certain model car, there should be more than 200 axles. All right, so now we want the probability that x bar is less than 595. Use normal CDF again, and this time you're going to have to change the standard deviation. So instead of 5.3, it's 5.3 divided by the square root of 20. And now we have a much smaller probability. It's only 0.0457. In other words, there's a 4.57% chance that the mean length of the 20 axles is less than 595 millimeters. All right, so we're done. Here are some optional practice problems for you. I recommend you take a look at them, but I'm not collecting them and I will not be grading them. If you have questions, all of these have answers in the back of the book, and you can certainly stop by during flex time or just ask me questions, send them to me. So I hope you have a good day, and I'll be seeing you in class on Friday.